All right, welcome back to Introduction to Speech Understanding. Again, this is lecture 13. This is the second to last lecture of the semester. So let's start out by going to the Intro Speech Understanding archive, wherever you have it on your computer, and fetching the release, and then merging the release with your local branch. All right, and now we should have a lecture 13 to go to. So let's go to lecture 13, and we see that there's a homework13.py and a grade.py and a lecture 13 notebook. So in order to find out what's going on, let's go ahead and start the Jupyter Notebook. All right, so this week we're continuing with the three lectures on speech synthesis. The type of speech synthesis that we'll be doing this week was actually originally developed for low bitrate speech coding. It's used these days. It's used for low bitrate speech coding in cell phones, and it's also used for voice conversion if you want to convert from a male to a female voice or between different kinds of voices. We're going to do maybe the simplest kind of voice conversion. We're going to use LPC in order to convert between a human-like voice and a robot voice by by making the voice completely monotone and by getting rid of all of the breathiness in the voice. First of all, let's go ahead and read in the data. This part of the lecture is really a repetition of things that have happened in the past. So first I'll read in the data from the file called speechwaveform.wave. That's actually a file that I've distributed to you in the past. That's just a recording of myself saying this is a speech waveform. So let me play it for you. This is a speech waveform. これは音声波形です. All right, so there's me saying this is a speech waveform. Let's create a spectrogram from it by chopping it into frames, calculating the magnitude, short time Fourier transform, and then calculating the spectrogram. And then we'll display the waveform and the spectrogram. Here's the waveform. This is a speech waveform, これは音声波形です. And you can kind of see where the syllables are. This is a speech waveform. Maybe これは音声波形です, or maybe これは音声波形です, something like that. I'm not sure exactly. We could probably see it down here. Let's see. Um, これは, so maybe this is これは onse. No, where's the S? Oh yeah, here's the S. This high frequency energy here is the S. So this is onse, and then the H must be around here. Hake des, something like that. All right, so there's the speech waveform that we're going to be working with this week. And what we're going to do is to analyze it using the same kind of resonant model that we had last time, and then resynthesize it using a robot-like voice. But before we analyze it, we have to chop it up into frames. So I've already done that. I've got this matrix called frames, which has frame length number of columns. Frame length is 25 milliseconds. If the sampling rate is, let's see, I set the sampling rate to 8,000 samples per second. So 25 milliseconds should be 25 times 8, or 400 samples. 25 times 8, I guess, is 400, 200, sorry, 200 samples. So the frames matrix should have 200 columns, and the number of rows will be whatever number of rows are necessary to take up 5.5 total seconds at about 10 milliseconds per frame. The frame skip is 10 milliseconds. So it should be about 55 rows and about 200 columns. That frames matrix, we're going to go through and basically choose and plot some of the frames. So let me choose frame number 200. That should be the frame that starts at about 2 seconds, right about here, the word wave. And then frame 230, that's the one that starts at about 2.3 seconds. So that's the word, the syllable form. And so if I run this code, I get the speech, and then I'm also plotting here the spectrogram. Let's see. Oh, yes, I'm plotting the spectrogram at frame 200 and the speech waveform at frame 200. So on the left side, I have the waveform. You can see that it's periodic with a period of about 10 milliseconds, meaning that my speech is at about 100 hertz, right? About 10 milliseconds per pitch period. And you can see the ringing of the first formant, and you can see that it's not exactly periodic with the period of the first formant. That's because there are other higher resonances that are not visible in the waveform. In the spectrum, we can see those easily. The jaggedness here is the pitch period. So the pitch has a frequency of about 100 hertz. So by the time we get to 500 hertz, we have one, two, three, four, five, maybe five peaks below 500 hertz. Then there's a big first resonance just below 500, another big resonance at about 1200 hertz. That's because this is the wave. Oh, this looks more like form, doesn't it? Well, the O for in form has a first resonance at about 400 hertz and another one at about 800 hertz. So that looks like form. This wave is not E-like; it's more like an ah or like an ah, actually. This is maybe it's supposed to be wave, but maybe it's halfway between the W and the A. So the second formant at about 1200 hertz is much lower than it would be for an E or an A. The third formant at 2500 hertz in both of these vowels. So you can see the peaks at about 500, about 1200, and about 2500. Here the peaks are at about 500, at about 900, and at about 2300. Those are the three formant resonances in both of those vowels. What I'm calling attention to is the fact that if we want to synthesize this entire sentence, we're going to have to allow those formant resonances to change with every frame. Every frame in the spectrogram is going to have a different set of formants. You can see them here in the spectrogram. In this is a, the first three syllables, this is a, have almost exactly the same F1 and F2. But as soon as I say speech, it has a very high F2 in the SPE, and then in the W it drops way down. Speech wave. So speech, and then the W drops F2 way down, and then going into wave, the F2 comes right back up again. And then for form, F2 is all the way down here at around 900 hertz. So you can see F2 is high, and then even higher, and then low and high, and then very low again. In Korewa, it's even more striking. The O in Kore is low, and the A in Kore is high, and the A in Wa is intermediate between those two. Korewa Onse, the O has a very low F2, the A in Se has a very high F2, the Hakke is in between, right? So you can see that the formants shift from one frame to the next. And if we want to resynthesize the speech, we need to somehow take into account that frequent changing of the formant frequencies. One way to do that is by analyzing the speech waveform in order to extract all those formants from it. And the easiest way to do that is to not worry about analyzing them separately, the way that we did last time. Instead, to model them all using just one big 10th order resonator. So rather than taking y of n equals e of n plus a1 times y of n minus 1 plus a2 times y of n minus 2, instead we'll just say s of n is equal to e of n. We'll use a minus sign. Minus or plus doesn't really matter. Minus a1 times s of n minus 1 minus a2 times s of n minus 2, and so on all the way back to order 10. And that allows us to model all four of those resonators, all with just one resonant filter with 10 feedback coefficients. Right? We're just going to feedback 10 times. In fact, four resonators really only needs 8 feedback coefficients, but we'll add 2 more just to make sure that we get everything. So we'll round it up to 10 feedback coefficients. I could go through the math of how do you derive these coefficients, but in order to do that, you would need some calculus. And so I'm going to skip over that and not use calculus. Instead, I'm going to say, let's use librosa.lpc. Those of you who have had calculus can look online on Wikipedia to learn how calculus is used to derive these coefficients. But for our purposes, let's just use librosa.lpc. What that does is it will take every single one of these frames and calculate the 10 corresponding coefficients. So this is the line that matters. I'm going to take librosa.lpc. Oh, let me look up librosa.lpc. Here's the help page for librosa.lpc. This uses a method called Berg's method, which guarantees stability. There are lots of different methods of finding the LPC coefficients. The simplest method is to simply calculate the squared value of E of n and then differentiate it with respect to A of k. And that gives you the equations for A of k. But even simpler than that is to use code that somebody else has already written. So we'll use librosa.lpc, which will analyze every single row, every single frame of this frames matrix with an order 10 LPC. And then I'm going to plot them. In axes 0, 0, I'll plot the 200th frame. In axes 0, 1, I'll do a stem plot of those coefficients for the 200th frame. So if I run this, I get then the waveform of the 200th frame, and you can see that it's resonant in this way, and the coefficients of the 200th frame. Now here's something that is a little bit different from what I described before. I said that there were 10 coefficients, but here in this plot you can see 11, from 0 to 10. And that's described in the text down here. If we wanted to find E of n, right, I said back up here that S of n is E of n minus the sum of 10 delayed versions of S of n. That means that we can get E of n back again from S of n by taking S of n plus the sum from k equals 1 to 10 of A of k times S of n minus k. And Librosa sets it up so that A of 0 is always 1. You notice that the other coefficients have very different magnitudes in these two vowels. For the A, these coefficients have magnitudes that are always less than 2. For the O, these coefficients have very large magnitudes, sometimes plus or minus 5. But the A of 0 is always a 1. And that's designed so that rather than using this first equation, we can always just use the second equation. We can always take A dot product with the time-flipped version of S. Right? So this is actually a dot product between the A vector and a time-flipped version of S. I'm not going to use the np dot dot function for this, but you could use np dot dot. What I'm going to do is I'm just going to take the excitation and set the excitation equal to zeros. And then I'm going to take, for k in the range from 0 to 10, right? Range 11, so that's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to take the excitation of the current sample and add to it A of k times frames of sample minus k. So for every sample, the excitation is going to be the sum from 0 to 10 of A of k times S of n minus k. And when I do that, here's what happens then. I discovered that the speech waveform has a lot of structure, a lot of information about the formants. This is a lot of information about exactly what vowel it is. But the excitation doesn't. The excitation is basically a sequence of impulses. There's a lot of little noise down here, a lot of very low amplitude noise, but the only really high amplitude information is one impulse every pitch period. Notice that these two impulses are, let's see, this one is at about 8 milliseconds and this one is at about 17 milliseconds. So these are about 9 milliseconds apart. This one is at about 6 milliseconds, this is about 15 milliseconds, and this is about 24. So these are again about 9 milliseconds apart. And you can see that they correspond exactly to the start times of each of the pitch periods. They correspond to that moment when the vocal folds close. And when the vocal folds close, there's a sudden negative spike of air pressure. And here we've flipped that negative sign upside down, so we're showing it as a positive spike instead of a negative spike. Right, so you can see that what I've done is I've just taken the excitation is equal to the sum from k equals 0 to 10 of a of k times the speech waveform at sample minus k. And that gives us the excitation is basically just a sequence of impulses spaced one pitch period apart. The other thing to notice is that different frames have different energy. In the word wave, the excitation has an amplitude of about 0.06. And in the word form, the excitation has an amplitude of just over 0.01. So these amplitudes are very different, right? That corresponds to the difference in the LPC coefficients. Basically, in the wave syllable, the LPC prediction doesn't account for as much of the energy. So both of these have a total energy in the speech waveform of about 0.3 is their maximum. A little bit smaller for form, but more of that energy is explained by the LPC in the syllable form than in the syllable wave. And so when I get down to the excitation, the LPC excitation for the syllable wave has to have a higher amplitude, 0.06, and the excitation for the syllable form has a much lower amplitude, like 0.01. So we have to represent that in some way. Other than that, they're basically impulse responses, which means that if we wanted to take this spectrum, right, and we want to smooth out all of this jaggedness because of the pitch and just keep the smooth version that shows F1, F2, and F3, we can keep that smooth version by just keeping the Fourier transform of the LPC coefficients. The LPC coefficients are inverse filtering S to get E, and so we can get the speech back again by dividing by the Fourier transform of the LPC coefficients. So we can take that LPC sequence, A0 through A10, and we can just treat it as a signal and take its Fourier transform, and then take 1 over that Fourier transform. And that gives us back again the speech transform, the speech Fourier transform. We need to scale it by the root mean squared energy. So we take E of n, this energy, square it, add up all of the squared samples, average, and then take the square root. And that gives us the root mean squared energy of the excitation signal. We divide that by the Fourier transform of the LPC coefficients, and that gives us the speech spectrum. So let me actually do that. Let me say that the LPC spectrogram in any given frame is 20 times the log base 10 of the gain for that frame, divided by the absolute value of the FFT of the LPC coefficients. So I'll just treat the LPC coefficients for each frame as if it was a signal, as if it was exactly the impulse response for one pitch period. But it's not the impulse response, it's 1 over the frequency response. The frequency response of the speech is 1 over the Fourier transform of the LPC coefficients. And so I divide by the Fourier transform rather than multiplying. And when I do that, I get, you can see here that basically what I get is a smoothed version of the spectrogram. All of the horizontal lines that correspond to pitch here are all gone. Instead, we just have a bright line where the first formant is, and another bright line where the second formant is, and a third bright line at the third formant, and a fourth bright line at the fourth formant. What LPC has done basically is it takes out the information that characterizes the vowel, and it gets rid of the information that characterizes the speaker, the information about the person speaking. So the pitch period, this information about who's speaking, that's in the excitation. And the information about which vowel it is, that's captured by the LPC. And we separate those two kinds of information. The pitch period is in E of n, and the information about what vowel it is in A of omega. So in that way, LPC is also a good method for speech recognition. We can use it for automatic speech recognition as well as for automatic speech synthesis. Let's actually use it for speech synthesis. Let's take E of n and pass it back through that resonant filter to get S of n again. Remember that we do this by taking E of n and then subtracting k equals 1 through 10 this time, not 0 through 10. just k equals 1 through 10, a of k times x of n minus k. Oh, this should be s of n minus k, not x. Let me change that to s. There we go. So we take e of n and then subtract the sum from k equals 1 to 10, not 0 to 10. The sum from k equals 1 to 10, a of k times s of n minus k, and that gives us back again the speech signal. And in fact, if you use the original excitation, this gives us something that's very, very close to the original speech signal. This is basically how your cell phone works. The speech coder on a cell phone constructs a really good model of E of n, and then passes it through this LPC filter in order to reconstruct the speech. So if I take that excitation signal, I can find out how many frames there are and how many samples in each frame. There are 556 frames, and the skip between frames is 80 samples. Each frame is 200 samples long. In order to reconstruct E of n, I started out with overlapping frames. Remember? These frames were overlapping. If I go back up here to where I calculated the frames, here we go. The frames are, right? The frames skip by only 10 milliseconds between frames, but the length of the frame is 25 milliseconds. And so they overlap by a great deal. And so in order to resynthesize the speech, the first thing I need to do is to get rid of that overlap. Here's LPC coding. Here's the synthesis. I need to delete the overlapping part from each frame. And I can do that by just keeping the last frame skip samples. So I can take frame length minus frame skip all the way up to frame length. Just keep the last 80 samples from each frame, right? I'll put a colon here in order to keep all of the frames. But from each frame, I'm only going to keep the last frame skip number of samples. And I'm going to concatenate all of those together to create the signal E of n. Total length is 44,480, which is 556 frames times 80 samples gives 44,480. And then I'm going to take that E of n and I'm going to create a synthesized speech waveform, which has the same length. And then for each of those synthesis samples, I'll set the synthesis sample equal to E of n. And then for k in the range from 1 to 10, notice not from 0 to 10, but now from 1 to 10. For k in the range from 1 to 10, I'm going to subtract a of k times the synthesis signal at n minus k. So for k equals 1 to 10, I subtract the feedback synthesis sample, and I get something that sounds like this. This is a speech waveform. これは音声波形です。You can hear that there's a little bit of echo toward the end, but really, really, this should sound almost exactly like the original waveform. I'm not sure if I can even tell the difference. They sound very similar. Let me see if we can hear the difference. This is a speech waveform. これは音声波形です。The reverberation is in the original recording. I think that the resynthesized speech sounds exactly the same as the original speech. This is a speech waveform. これは音声波形です。Yeah, so the resynthesized speech sounds exactly the same as the original speech. We took that excitation signal, we got that by inverse filtering the speech using LPC. And then we refilter the speech using LPC in order to refilter the excitation in order to regenerate the speech signal. And we get the original speech signal back again. So I could, for example, let's see, I'm not sure why it doesn't show the first frame. I could re-show, here's the original speech waveform and the original speech spectrogram. Here's the synthesized speech waveform and the synthesized spectrogram. And yeah, they look exactly the same. So now we know that if you have a really good excitation signal, you can resynthesize the speech exactly by taking that excitation signal and passing it through the LPC. That can be useful for practical purposes. If you're designing a cell phone, that can be a useful thing to do. But it's not very much fun if you're just playing around in Python. So let's do something that's a little bit more fun. Let's make a robot. In order to make a robot, we'll do two things. We'll take my voice and we'll take the vocal fold excitation and we'll get rid of all of the breathiness. So it will be just mechanical, just purely once every 10 milliseconds, there will be another impulse. And second, we'll make it a perfect monotone, exactly 10 milliseconds between samples. So I'll take fs over 100. That gives me how many samples. That gives me the pitch period in samples, right? I want a 100 hertz voice. And so I take the sampling rate, fs, divide it by 100, and set those samples equal to 1. And then the other thing I need to do is to multiply by the gain. So I'll take the gain for that frame and multiply it by the impulse signal P of n. And I'll do that for every n in the length of the P. I'll go through and I'll find which frame am I in. And I get that by taking n and divide it by the frame skip. So the first 80 samples are frame 0. The next 80 samples are frame 1. The 80 samples after that are frame 2, and so on. I'll multiply the frame's gain times this period sequence of impulses, and I'll call that the excitation. And then from that excitation, I'll subtract I'll sum from k equals 1 to 10, a of k times s of n minus k in order to produce the speech signal. And the result now should sound like my voice if I was turned into a robot.
This is a speech waveform. これは音声波形です。
So you can hear that it sounds like my voice, but turned into a robot.
This is a speech waveform. これは音声波形です。
It sounds robotic because there's no breathiness. It's purely mechanical, one pulse every 10 milliseconds. And it's also perfectly monotone, no change in pitch at all. We can do a lot of things with this. We can make it sound more female by just doubling the pitch frequency. From 100 hertz, we can make it 200 hertz, which is more typical of a female voice.
This is a speech waveform. これは音声波形です。
It's not very convincingly female, but you might say it's kind of a female-like robot. I wonder what happens if we make it 250 hertz. Let's try that.
This is a speech waveform. これは音声波形です。
It sounds more like some sort of space alien, I guess. Not particularly female, but anyway. We can also try to make it a little bit more meaningful by giving it a pitch period that changes with time. Let's make the fundamental frequency change, go up and then come down again. It'll start out at 200, go up and then come down again. So I'll create f0 and I'll say that f0 should be 200 plus 40t or 400 minus 40t, whichever one is smaller. And then t0, the pitch period, will be the sampling frequency, samples per second, divided by the pitch frequency in cycles per second. That gives us f0 going up in a straight line and then coming down in a straight line. T0 goes down and then comes up again. It's not quite a straight line because it's 1 over a straight line, right? And now I need to figure out how to take this T0 and make this the spacing between impulses. And what I'm going to do is I'm going to start out with E robot just a set of zeros, right? And then I'll set n equal to 0. And while n is less than the length of the total excitation, I'll set that excitation equal to the gain of the current frame, right? The current frame is n over the frame skip. And then after that, I will add to n one pitch period. Whatever the current pitch period is, t naught of n, I'll add that to n. So all of the samples in between, I'm just leaving as zeros. And I'm only creating a sample once every t naught. The results look something like this. Here's the total excitation. It's always positive because these are always positive samples. Here's the excitation in the 200th frame. Here's the excitation in the 230th frame. Right? Notice that in the 230th frame, the pitch frequency is higher, and so the pitch period is a little bit shorter. Let's listen to hear what it sounds like.
This is a speech waveform. これは音声波形です。
So we get this artificial, kind of creepy sounding robot voice, right? The pitch goes up and then it comes down again.
This is a speech waveform. これは音声波形です。
And you can do all kinds of tricks. We could add some random excitation to this. I'm not sure if this is going to work. Let me try it and find out. Let me just add np.random.rand n 1 times 0.0005. I'm not sure if this will work or not. Let's find out. Nope, that didn't work. Oh, did it?
This is a speech waveform. これは音声波形です。
Hmm, it's almost inaudible. How about if I make it 10 times louder and see what happens?
This is a speech waveform. これは音声波形です。
Oh, now it gets kind of hoarse sounding rather than breathy. So you can play all kinds of games, make it more hoarse or more breathy, change the pitch in the way that you want. For the homework, we're just going to do the three parts of the lecture. We're going to do LPC analysis, LPC synthesis, and creating a robot voice. So let's analyze these three things. First of all, let me go ahead and open up the homework, homework13.py. So the first section, we want to perform linear predictive analysis of the speech. We're given a speech waveform which has duration number of samples. We're given a frame length in samples, say 200 samples, a frame skip in samples, say 80 samples, and the order of LPC. This tells it in the entire lecture so far, we've set order equal to 10. How many coefficients do you want? And it should return a coefficient matrix with a number of frames, number of rows, and then with 11 columns. And it should return the excitation signal, right? So the first thing we need to do is to just chop the speech up into frames. So this is going to be something like we'll calculate an array, and that array will be speech of m times the frame skip up to m times the frame skip plus the frame length, or m in the range from 0 up to the integer of length of the speech minus the frame length divided by the frame skip. All right, that gives us the number of frames. Actually, why don't I specify that separately? The number of frames should be integer of length of the speech minus the frame length divided by the frame skip. There we go. And then we can just use that here. M goes from 0 up to the number of frames. All right, that gives us the frames. And now we want to calculate the LPC on those. And for that, we can just type Librosa LPC on the frames with order equals to the order. All right, now we've got the frames divided, and we've got the LPC coefficients. Now we want to create an excitation signal, which is n frames rows, and each frame is the frame length samples. And only the last frame skip samples need to be valid, so we can skip the first 10, which is good because we're going to create each sample by looking at the 11 previous speech input samples. So for, let's see, m in the range up to n frames, so for each frame, for sample number from, let's start with sample number 11 and let's go up to the frame length. And for each of those, we're going to take delays from k in the range from 0 up to the order. Oh, let's call this from order up to frame length, and this will be from range from 0 up to the order. We will say excitation. Oh, the excitation needs to be created first. Excitation will start out as all zeros. And of a size, the number of columns is frame length, right? All right. And then to that 0, we will add the coefficient in the mth frame and the kth delay times the speech signal in the mth frame with n minus k as the delay. That should give us the whole excitation. So that now let's return A and excitation. There we go. So we've calculated the LPC coefficients with an order equal to 10 or whatever we specified. We created the excitation as an all zeros matrix. And then for each frame, we took the samples from order up to frame length. And for K in the range from 0 up to order plus 1, we need, if the order is 10, we need to go up to 10, not up to just 11. So maybe this needs to be order plus 1. It shouldn't matter. Right, so for n in the sound, n ranging from 11 up to, actually, let's see. If n starts as order, and if this goes up to order, then we start out with sample, we go up to sample order minus order is 0. That should work out. For k in range 0 to order plus 1, excitation mn is that sum. Let me save this and try it out and see if it works on the sample. All right, let's run homework13.lpc help file, and let me run homework13.lpc and get back the LPC coefficients, and then I'll calculate the LPC spectrogram here and plot it. Let's see if this works without an error. Yep, looks like it worked. And I got back again the LPC spectrogram. This is actually a really sensitive. If you get if you add over especially in the, I mean, I did some of this while I was preparing this assignment. If this K adds over the wrong sequence, if you add only from 1 to order plus 1 or only from 0 to order, then you get a spectrogram that doesn't look as good. And so this is a good debugging tool. If the spectrogram looks really sharp like this, that means that you've got everything correct, including exactly the correct range of samples to add over. All right, the second thing we want to do is to resynthesize speech. We're given an excitation signal, which is just one long vector of length duration. And we're also told the frame skip. And then we're also given the coefficients. A goes from n frames up to order plus 1. So we'll take, we assume that we have the excitation. So let's actually go synthesis. We'll start out with that equal to, let's actually start out with that equal to the excitation. That will be a nice way to start. And then if we start with synthesis equal to the excitation, then we can do for n in the range up to the length of the synthesis. We will calculate which frame it is. The frame is equal to the integer of n over the frame skip. And then we want to do for k in the range now from 1 up to order plus 1, not from, order is not specified here, so I guess we'd better make it 11. We want to do for k in the range of 1 up to 11. And actually here, this sample number n might be less than 11, so we'd better make this the minimum of n or 11. All right, so for k in the range from 1 up to minimum of n or 11, we want to take the synthesis and subtract from it a of frame comma k times synthesis of n minus k, and then return the synthesis. All right, so we took for n in the range up to the length of the synthesis, we started out with the synthesis just equal to the excitation. Then for n in the range from up to the length of the synthesis, calculate which frame we're in. And then for k in the range from 1 up to minimum of n or 11, we take synthesis of n and subtract from it a of the kth coefficient times the n minus kth synthesis sample. Let's try that and see if that gives us good results. Here we'll look at the doc string specifying what we should do, and then let's try synthesizing speech and see how it sounds. Notice I just stacked up. I took the last 80 samples from every frame here and called those E, and then I passed in E to the synthesis, and the result sounds like this. This is a speech waveform. これは音声波形です. So that worked well. Good. This is a little bit tricky, right? Getting exactly what is the range over which this k should be summing. That's a little bit tricky. And so you can really debug if you've got the right range by listening to it and see if it sounds right. And that tells you if it sounds right, that means you got the right range. If it sounds wrong, that means you probably got the wrong range somehow. Finally, let's create a robot voice synthesis. We'll take the excitation frames, and rather than passing those directly back into the LPC, we're going to calculate the gain from each frame. And then from those gains and from a scalar pitch period, whatever pitch period we want, 100 hertz or 200 hertz, fs over 100, fs over 200, we will calculate a robot excitation. All right, so, and frames, why is it caps locked? And frames, frame length should be the shape of the excitation. Now we know how many frames there are. And now, I'm not sure if I really needed that, but let's create a gain vector, which is n frames long. And then for each of the frames, I want to say that the gain vector for that frame is equal to the square root of the average of the square of the samples in that frame's excitation. So I square the samples, average them, and then take the square root. Once I've got the gains for each frame, then I want to create the robot excitation. And let's start out with it being number of zeros equal to number of frames times the frame skip. Right? That's what it specifies there, that it should be that many samples long. And then let's do that trick that I did in the Jupyter Notebook. I'll set n equal to 0 initially. And then while n is less than the length of the excitation, I'll set E of n is equal to the gain of the frame. Okay, the frame number will be n over frame skip, right? And then I'll set n plus equal to the pitch period. The pitch period actually is not varying as a function of time now, it's just an integer. But this way, I'm only going to set E of n to something non-zero if n is a multiple of t naught. Right? You could do it the same way that I did in the assignment in the Jupyter Notebook. You could set E of n equal to an impulse train and then scale it. But here, this is another way to do it. Now I want to just return the gain and the robot excitation. All right, I think that should be all I need. Let's check and see if that works. Here's the help doc string for the robot voice. And then I'm going to create a robot voice with a 100 hertz pitch frequency. And with the excitation frames that I specified before, those should give me the gain. And so if I run that, I should get I got an error. E of n is not defined. Oh, this should be E robot of n, shouldn't it? Because that's what I'm trying to construct, E robot. All right, let's try running it again. Okay, so I created the gain in the E robot, and then I created S robot by passing E robot as the excitation, and the result sounds like this.
This is a speech waveform.
And there we go. We've got our robot voice. Let's grade it and make sure that it matches the what the grading code says it should be. Oh no, what happened? 2 successes out of 3 tests. Self-assert graded greater NP average n square synthesis over absolute value of E. Synthesis power should be greater than excitation power. Well, maybe that didn't happen. Maybe the synthesis power was not greater than the excitation power. I'm going to say if you get that particular error, don't worry about it. Make sure that make sure that it sounds good in the Jupyter Notebook. And if it sounds good, go ahead and check it in. I'm sorry, I'm not sure why it's throwing that particular error. If we look into grade.py, we should be able to find out where the error is coming from. It's coming from this assert greater than. It's saying that the average of the squared synthesis samples is not greater than the average of the squared excitation samples. Um, okay, I don't know why not, but let's not worry about it. Let's go ahead and check that in. Let's go ahead and start up GitHub Desktop. As long as it sounds good in the Jupyter Notebook, I would say go ahead and check it in, and um, and if everything seems to be in order, then that will be given full credit. So we'll go ahead and check it in, and then let me go to github.com. And let me change from my teacher account to my student account. And then if we look into the intro speech understanding, look under lecture 13, look under homework 13.py. There we have the full code representing everything that worked well in the Jupyter Notebook. So go ahead and copy that and then go to the course, to homework 13, which is not yet created, and check it in there. Let me go ahead and create homework 13 for you right now so you can watch me doing it. We create an assignment, and this assignment should be called homework 13, and it should be due February 28th, I think. And we should allow unlimited attempts. You can try it as many times as you want. And the points will be 100, and that's everything. Go ahead and create that. Oh, and let's say enter the URL of your copy of homework 13.py. We'll save that. So go ahead and let me make it visible to students. There we go. Go ahead and enter the URL of your copy of homework 13.py. And once you've entered that, I'll go ahead and check it and grade it. That's all visible now. So that's everything. Let me turn off the recording and then we'll go ahead and take attendance.